All right, let's solve another question. This time it is question 113. So in question 113, we're given this diagram. It's a bit different than the previous problem. This time there's two power supply. And note, they are pointing in opposite directions. So it's a bit tricky right away how we can deal with such a problem. We cannot use the previous simplification because of the two power supply. We will need to use Kirchhoff law. There's two Kirchhoff law. There's the loop rule. The loop rule states that the sum of the voltage gain and voltage drop across a closed loop has to equal to zero. The junction rule tells us that the current coming into a junction has to equal the current coming out of a junction. Well, this one is really nearly a series circuit, except for the fact there's two power supply. There's no junction. The current going through each of the power supply and the resistance is the same here. So we will need to use the loop rule. So the loop rule, the way we solve the loop rule is we start at a certain point, go around a closed loop, end up at the same starting point, and in between we add all the voltage gain and the voltage drop. Now, we will need to make an assumption here. We're going to need to make an assumption on in which direction the current is flowing. And note, it does not matter if we are wrong with our assumption. You will see at the end, we will know the right answer. So we will assume that the current is flowing in that direction. Okay, so the current is going up. Now, let's have a look at each resistance. If the current is going up here, that means we have a voltage gain here, and note it's going from the negative to the positive, so we have a voltage gain. Then it goes through the resistance. Well, if the current is going that way, a charge always has more energy when it enters the resistance than when it leaves the resistance, which means the voltage is higher on that side than on this one. So plus, minus, plus, minus, plus, minus, plus, minus. There's a voltage drop on each resistance in this case. All right, so we start here. We have plus 10 volt. So 10 volt. We have minus the voltage drop here. Now we don't know the voltage drop, but we can replace it with its Ohm law equivalent. So it's equal to minus the current multiplied by the resistance. So it's 10K. And I'm gonna write 10K in this case. Now obviously, well actually, no, I'm not gonna do it. I'm gonna write 10,000. It's easier that way. So same logic for this one. So minus I 20,000 minus I 10,000. Then this is one of the tricky part. We are going in reverse from that power supply, so it acts as a voltage drop. We're going from the plus to the negative. So minus 24. Again, another voltage drop here, minus I 10,000 and minus I 10,000 again. All right, so we got, in all of this has to equal 0. So we got 12 minus 24, we got minus 12, minus 60,000 I equals 0. Let's isolate the voltage, the current over here. Just want to make sure I don't make any mistake. And we get minus 0.002 amp in this case. Now note, there's a minus here. The only thing this minus is telling us is we made a mistake in the direction of our current. The current is not going upward. The true current is going the other way around. And when you look at the diagram, it makes complete sense. We got this power source, 24 volt. We got this one, 12 volt. Well, you have two pumping in opposite direction. They are fighting each other. And there's one that's twice the strength and twice the energy of the other one. Well, obviously that one's gonna win. This one is going to pump way harder than that one. So the charge are going the other way. So the minus only tell you that your original assumption was wrong. Still, you're able to solve the problem. It does not matter, all right? Now, we want to find the voltage drop across each resistor. And at this point, basically, we voltage drop and power supply to the circuit and power dissipated by the circuit. So basically, we are going to write down the Ohm's law table again. I'm gonna write the total current on the top over here. So IT is equal to 0.0002 amp. And I'm going to erase that one. We're going to create an Ohm's law table. Now note this one. We will have, so R, I, V, P. And we got R1, R2, R3, R4, R5. I'm gonna, because we're not talking about equivalent resistance in this case, I'm gonna add the current going through each power source. So we got V1 is the 12 volt over here, V1 and V2, and you will see why I'm doing this by the end. All right, let's write down the value. Obviously, my square of it are a little bit small, so I'm just going to write 10K, the logic being the same. So R2 is 20K, and all the other one are 10K. All right. So obviously, there's no resistance for V1 and V2. It's only a voltage gain. So V1 in this situation. So here's the irony. Because the current is going that direction, the voltage V1 will be negative. Now I will explain that term before the end of the video. V2 will be 24 volt. We got our current. I'm gonna write, well, I'm gonna make it, actually I'm just gonna write we know that it's 0.0002 amp. So it's all the same current for all the power source and each resistor in this case. So I got 2 volt over here, 4, 2, 2, 2. Note 2 plus 2 plus 2 plus 2 plus 4 is equal to 12. Now what's happening, and I'm never going to try to trick you in a test, okay? But we have the current going into that direction. That means there's current going into the battery. In this situation, that means we are not, this battery is not supplying power. It's taking power. We are charging the battery, in fact. So because the current is going in the opposite direction, this one is charging. I'm never going to trick you in a test. It's possible that a battery might be charging, but I'm not going to ask you the question to memorize that part, okay? Because not all power supply can take power in the reverse. We are going simply to assume that, okay, it's going in the reverse direction. It does not matter, okay? Just to highlight that this can happen and it does not matter. All right, we need to find the power. So basically this is 0.0004 watt. This one same logic, except it's twice that amount, 8, 0.0004. Now note the voltage over here will be negative. I'm not gonna write the negative for the power, but the same logic apply for. Now note the power here, if we add all of them, including the power on V1, has to equal the power supply by V2. So that's part of the catch I was saying. This one is not a power supplier, it is a power consumer in this case. All right, so that's it for question 113. I'm going to be solving a couple more examples involving Kirchhoff law. These questions can get quite tricky and I want to make sure you get some good practice with them. So see you in the next video.